Good evening and welcome to Lowell Observatory's year-long celebration of the Lowell Discovery Telescope. My name is Kevin Schindler and I'm the Historian and Public Information Officer here at Lowell Observatory. And it's been such a wonderful year celebrating one of the world's most powerful telescopes. And we've throughout the year, every month, we've had different participants from Lowell Observatory and some of our partner organizations. And we've talked about a lot of things that make the LDT, the acronym we use for Lowell Discovery Telescope. We've talked about a lot of things that make it so special. There's the instrument itself and what it took to build this thing. There's the instruments that we use on it, a variety of telescopes. The telescope collects the light, but the instruments are the things that analyze it. So we talked about those. And a couple months ago, we went through the process of recoding a 14-foot diameter mirror, which is the primary mirror of the telescope. And then, of course, the most important thing we've covered is the variety of science that's being done with the telescope. And it's really quite a range. We started the year talking about solar system stuff, planets and moons and small bodies. We moved out, went to stars, star clusters and things like that. And tonight, we're going to go even further out. We're going to go beyond our galaxy and talk about really some of the most dramatic, cool things that happen in the universe that we've been able to detect. Things like related to supermassive black holes, something called tidal disruption events. We're going to talk about gamma ray bursts. And we're also going to talk about a new instrument that's being developed that's going to allow us to study a lot of this stuff. So we've got a great panel tonight of folks to talk. Throughout the year, we've heard from a lot of Lowell scientists, but something we want to make clear is, Lowell Observatory owns the telescope, but we have several institutional partners, and each one of those partners, their scientists, their faculty, their students have access to the Lowell Discovery Telescope. And so any given day, there's an announcement of one or another from one of our partners or Lowell of some important work being done with the LDT. Our partners include Northern Arizona University, Boston University, University of Toledo, Yale University, and I won't say the best for last, I don't want to insult anybody, but because our ties tonight have University of Maryland ties, that's our fifth partner. And so it makes it for a real vibrant scientific pursuits to have a lot of different partners, to have the Lowell team using one of the world's most powerful telescopes. And so what I'd like to do is first introduce each of our participants tonight, and then each one of them will tell a little bit about their research, particularly how they use the LDT for it. And then we'll also at the end have a little time for questions and answers. So for those watching, at any point, if you have a question, you can just send it in and we'll try to get to it at an appropriate time. So let me just introduce our participants tonight. First of all, we have Erica Hammerstein. She's a fifth-year PhD student at the University of Maryland. As a member of the Zwicky Transient Facility Collaboration, her research focuses on understanding transient phenomena related to supermassive black holes, with a primary interest in characterizing tidal disruption events at optical and ultraviolet wavelengths, in addition to studying their host galaxies. In her free time, which as a PhD student probably isn't much, she enjoys playing video games and crocheting. Today she'll be discussing how the LDT has helped to build one of the largest samples of optically selected tidal disruption events. And I introduced some terms there that may or may not be familiar, but Erica and our other panelists will kind of define those as we go on. And Erica, we were just talking that Erica's aunt was here just a few years ago because she's kind of an astronaut in training, Heidi, who was here in Flagstaff for training in the geology fields as well as up here at Lowell Observatory. So it's nice to continue the family collaboration with the Hammersteins. Our second presenter, Brennan O'Connor, is a sixth-year graduate student at George Washington University and the University of Maryland College Park, with a planned graduation in the spring of 2023, which is just around the corner. So you clearly have no free time either. right now. His work covers a broad swath of time domain astrophysics, including fast radio bursts, high mass X-ray binaries, cataclysmic variables, kilonova, short gamma ray bursts, and peculiar long gamma ray bursts. Today he'll be discussing LDT's observations of short gamma ray bursts, host galaxies, and follow-up observations of other interesting transients. Thanks for having us. Thanks for joining us tonight, Brendan. And then our third participant, Dr. Brad Cenko, is a research astrophysicist at NASA's Goddard Space Flight Center and an adjunct associate professor in the Department of Astronomy at the University of Maryland, College Park, one of our partners, of course. He studies gamma ray bursts, supernova, tidal disruption events, and other explosive transients. This is just going to be a great conversation tonight, I think. He's also the principal investigator of the Neil Gehrels Swift Observatory, a NASA satellite that observes these objects at gamma ray, X-ray, and ultraviolet wavelengths. So thanks, Brad, for joining us tonight, and thanks for gathering Erica and Brendan in their spare time, which I guess you guys have more spare time than we thought, if you can come on and join us. So we appreciate you taking the time. So let's start off with you, Erica, and hear about your research a little bit and how you use the LDT.
Yeah, thank you. So today I'm going to be talking a little bit about my research on tidal disruption events, how we classify them, how we find them, and a little bit about their host galaxies. Okay. So to start, my slides will progress. There we go. I want to talk a little bit about what a tidal disruption event actually is. It's thought that nearly every massive galaxy has a supermassive black hole lurking at the center. And sometimes these black holes don't exactly get along with the stars that are also at the center. And a star can be kicked into an orbit that brings it within the tidal radius. And this means that the star is going to experience tidal forces that distort it, that stretch it, and eventually shred the star apart. This stellar debris half of it will be flung out into the circumnuclear medium, and about half of it will become bound to the supermassive black hole. And it'll form what's called an accretion disk. And that accretion disk, the matter in the accretion disk will eventually become available to fall onto the black hole and feed the black hole. And this process creates luminous flares of radiation that we can observe from Earth, even in other galaxies. These objects are interesting for a variety of reasons. They're just plain cool, but they also give us a lot of information about how black holes work, about the connection that black holes have with their host galaxies, about cosmology. And there's plenty of things that TDEs can help with. One thing is that there's a pretty large population of supermassive black holes at the centers of galaxies that are either too far away for us to observe their influence on their host galaxies, or they're not actively accreting anything, and so they're not bright and we can't see them. Tidal disruption events offer a way for us to see these distant or dormant black holes. They kind of act like cosmic signs for these black holes at the centers of these galaxies. The other cool thing about tidal disruption events is that they actually give us the chance to study the phases of black hole accretion, supermassive black hole accretion, on human timescales. So normally for a supermassive black hole that's accreting, we don't typically see it go from quiescence, so where it's not actively consuming any sort of matter, to rapidly consuming this matter in such a short period of time. And for tidal disruption events, this happens on the scale of months to years. And so we're actually able to observe that. Now, how do we actually discover these objects? So I'm a member of the Zwicky Transient Facility collaboration. And we use the Zwicky Transient Facility, and it's located at Palomar Observatory in California. And it's a collection of a few different telescopes. And I mentioned that these flares of radiation that we see from tidal disruption events can be observed from Earth. And survey telescopes like ZTF are a great way to actually do that. So we use the P48 for the discovery of new tidal disruption events. There's also a few other telescopes that we use for follow-up and classification, but the P48 is where most of the action in ZTF happens. So once we discover new objects that we think might be tidal disruption events with ZTF, we can then follow them up with the Lowell Discovery Telescope. Now, this is just a little sample of the kind of information that we get from ZTF. So every night, the ZTF P48 telescope will take pictures of the sky, and it'll compare those pictures to older pictures of the same parts of the sky. And if you subtract those from each other and there's something left behind, so you can see here, this is the new image, this is the old image, and then this is the subtraction of those two. If there's something left behind, then that's a new transient that we are potentially interested in studying. Now, because ZTF is taking images of the same field every few nights, we also get light curves, and that tells us how the brightness of these transients are changing over time. And this is kind of a cool little movie of all of these images, one after another. You can see that the transient, which is at the center of the image, changes in brightness over time. And I think if you watch, there might be a little maybe solar system object moving through one of the frames. Yeah, so this is how we discover, this is what it looks like when we get a new transient in ZTF. Now, tidal disruption events are not the only transients that occur in the centers of galaxies. We have a few other imposters that might look like tidal disruption events. And we have to weed those out before we actually get to do some of the cool TDE science. And these imposters are mostly going to be nuclear supernovae and active galactic nuclei. The way this typically works is we get candidates from ZTF. So we get the light curves, we get potential new TDEs, we also get the imposters. And we can take those to LDT, and we typically use the Divini spectrograph on LDT to take spectra of our candidates. And the spectra will tell us a few different things about the candidate in question. So it can tell us what elements are present in this particular object. It can tell us the temperature of the gas and the dust and the matter that's involved with the transient. And it can also tell us how far away the transient is. We have a pretty good idea of what supernovae and AGN and tidal disruption events all look like in their spectra. And luckily, they're pretty different. So in this middle figure here, I'm showing a spectrum of type 1a supernova in the blue, and then in the orange here, I'm showing a spectrum of an AGN, an active galactic nucleus. And then on the bottom, I am showing a tidal disruption event. So you can see that they're all fairly different, and this is what it looks like when we try to classify new unknown transients. We get a spectrum that looks like this, and we can compare it to what we know about them to figure out if it's a tidal disruption event or something else. So by doing this, we have been able to discover and classify over 70 tidal disruption events just with ZTF alone. And many of these have been classified as TDEs due to the help of LDT and the Divini spectrograph. And this is the largest sample of systematically discovered TDEs from a single survey ever. So this is a really amazing thing that we're able to do. And it's really great that we have the resources the spectroscopic resources to be able to follow these up and find this many TDEs. Our observations with LDT have also enabled us to further classify tidal disruption events by their spectra. And until recently, it was thought that there were 3 types of tidal disruption event spectra. So it was thought that there were some that had hydrogen lines in their spectra, which is the red one here. It was thought that there were also ones that had just helium lines in their spectra, which is this blue one here. And then there were a few that had a combination of both. But over the past few years and with our observations from Divini, we've been able to actually discover a 4th class of tidal disruption events. And it's this black one down at the bottom. And those actually don't show any sort of hydrogen or helium emission lines in their spectra. So this is brand new. It's a fairly recent results, and it's pretty exciting. Now, another thing I'm interested in surrounding tidal disruption events are their host galaxies. And I'm interested in the environments in which tidal disruption events occur, because understanding these environments can help us understand the tidal disruption events themselves, as well as the mechanisms that cause them. So by observing tidal disruption event host galaxies and obtaining spectra of them, we can compare their stellar populations to what we would consider normal galaxies. So galaxies that are not known to have hosted tidal disruption events. And we actually find some pretty interesting things when we do that. So in this figure here, I am showing a sample of normal galaxies, and those are in the gray contours. And then the colored dots are tidal disruption event host galaxies. And what we're looking at is a comparison between two features in their spectra. So this is an absorption line of hydrogen and an emission line of hydrogen, similar to the lines that I showed on the previous slide, although this one is of the host galaxies and not the tidal disruption event itself. So we find that many of the TDE hosts are not like most normal galaxies. A lot of them occupy these boxes down here, which highlight a fairly rare type of galaxy known as a post-starburst galaxy. And there's a few reasons why this might be. These post-starburst galaxies are pretty centrally concentrated, and it's possible that this property causes more stars to be available at the centers of these galaxies for the supermassive black holes to actually disrupt and tear apart. It's also possible that it complicates the dynamics of the centers of these galaxies. So the stars, since there's more of them in the center, they have more complicated interactions, and more stars are being kicked into the center for the black hole to eventually tear apart. So these types of observations are helping us understand why some galaxies are more likely to host tidal disruption events than others. So that was just a general overview of the kind of research I do with LDT, and I'm really excited to have a discussion about it.
Well, thanks, Erica. And we'll have some more Q&A at the end, but we have several questions that are probably appropriate to ask now.
Sure.
So let's just go through these, and then if we have more come in, we'll get to those a little bit later. First of all, with you talked about discovering these with the ZTF and then characterizing with LDF or LDT. What makes each of those instruments appropriate? The ZTF for discovery and then the LDT for follow-up.
Yeah, so ZTF is it's a survey telescope, and so every night it scans the sky, and these tidal disruption events are evolving on a matter of days to weeks. And so to really understand how they evolve and actually be able to see the flare of light itself, we need to be able to scan the sky every few nights. And so ZTF is really great for that. The other reason ZTF is good is because it gives us color information. So it takes images in a few different filters, and the G and R filters are the ones that we use, and those are visible filters. So by comparing how much light is in each of those two filters, we're able to get a sense of what the color of the transients are. And when we look for TDEs, we're looking for things that are blue. So having those two filters is really helpful for being able to find these objects. LDT, on the other hand, is really helpful for actually confirming that they're tidal disruption events. And we mostly use the Davini spectrograph, and it's an optical spectrograph, so it's in the perfect wavelength range to be able to study those lines that I was talking about. It also it's helpful for being able to resolve some of those lines. Some of the lines can be faint, some of them can be narrow. And so it's better than using a lower resolution spectrograph. Yeah.
Okay. Let's go through a couple more. Does a star feed the black hole? Whoops, I just lost the comment there. We could talk all night about black holes. This is like dinosaurs, right? Black holes and dinosaurs are like so cool. You could talk all night. Does a star feed the black hole, and when does it become filled?
Yeah, so any matter that falls onto the black hole is going to add to the mass of that black hole. We typically think of tidal disruption events. Any matter that the star feeds onto the black hole can't be more massive than the star itself. So when we think of tidal disruption events, we're typically thinking of a solar mass. In the grand scheme of supermassive black holes, that's not very much mass that's actually added. But yeah, so that stellar debris will eventually become part of the black hole itself.
Okay. And then a couple of questions from Chris. As the TD occurs, is the material generally ionized and are signals strongly polarized in a diagnostic manner?
Yeah, so the material is definitely ionized. As far as polarization, that is actually something that I don't think has been done very often in TDE studies. And that's something that's a new avenue that I think needs to be explored. But yeah, hopefully we'll be able to get some more information on the polarization in the next few years. But it is the material is definitely ionized, yeah.
Okay, and then one more question from Chris, and then we'll move on. Do the featureless variety represent black body radiation of unionized matter?
Yeah, so we don't actually know yet why some of those tidal disruption events are featureless. I mentioned that that's a pretty new discovery. So it's not entirely clear why they don't show features in their spectra. We found that the featureless tidal disruption events have higher black hole masses. So it's possible that whatever is creating those lines in the spectra is sensitive to the black hole mass. But yeah, it's not entirely clear yet why that is.
This is exciting. You've discovered so much, but there's so many more things to learn, as often happens with this sort of thing. So it sounds like you have a whole career ahead of you once you finish that PhD thing. Well, thanks, Erica. Let's move on to Brendan. We'll hear about short gamma ray bursts and some of your research.
Yeah, thank you. Okay. So yeah, I'll be talking about host galaxies of gamma ray bursts. So similar to Erica, identifying and figuring out what's going on in the galaxy can tell us a lot about the sources we're observing. So first, I'll discuss what is a gamma ray burst. So a gamma ray burst is essentially, there's two ways to produce them. One is the collapse of a massive star forming a black hole, and then there's these sort of jets of material moving towards the speed of light and very, very, very fast. And they come out both sides of this engine, but because they're really narrow on the sky and they're beamed very, very highly, we only see one side of the jet, the one that's pointed directly at us. And here's sort of a schematic. So we have this new formed black hole. There's some matter that accretes onto it, similar to what Erica was talking about. And then it sort of spits out that material moving really, really, really fast. And this is what we see, producing the initial gamma rays, which the Neil Gehrels Swift Observatory or Fermi Gamma Ray Burst Monitor will detect. These gamma ray bursts have many different durations. We classify them as being short duration if they're less than 2 seconds, and longer duration if they're greater than 2 seconds. But we don't just see the gamma rays, we also have the interaction between this jet and the surrounding material, gas and dust within the galaxy. And the interaction between the jet and the material actually emits across the electromagnetic spectrum from gamma rays to radio waves. And we can learn a lot by studying these afterglows, and which is that interaction. So I discussed how gamma ray bursts are caused by the collapse of massive stars, but actually on August 17, 2017, there was a groundbreaking discovery that there was a system of binary neutron stars that merged, and this was detected in gravitational waves by LIGO Virgo. We see here in the middle panel this sort of in-spiral signal. As the system begins moving closer together, the frequency is increasing, and eventually the systems merge here. So 1.4 seconds later, these green lines show Fermi and integral detections of a short duration gamma ray burst associated to this gravitational wave merger. And we know that they were associated because of the duration, but also the fact that they were localized to the same region of the sky. And in fact, astronomers were able to pinpoint even more precisely on the sky where this event happened. And we see here on the left a video of observations from the Neil Gehrels Swift Observatory UV and optical telescope. This is the transient being detected and then fading away over time. This initial detection is actually a really new transient as well. So not only did this gravitational wave signal was the first detection of two neutron stars merging, but also this new transient called a kilonova, which is in the optical and infrared wavelengths. This kilonova is powered by the radioactive decay of heavy metals like gold and platinum and things like this that are decaying and heating up this material that's been ejected in the merger and producing this infrared signal that we see. And it's just a really, really fascinating event, and we're hoping to find more of them in these upcoming gravitational wave runs. So on the right, we see a more precise or higher resolution image of the GRB and its afterglow and kilonova, the localization here shown by the white circle, and this source here fades away over time, and the galaxy in which it occurred in. And if we look at the galaxy, there's a few takeaways. One is that it's much brighter towards the center. So there's more stars in the center of the galaxy and less stars as you move away as the light becomes more diffuse. And the other takeaway is that the distance between the GRB and the center of the galaxy is quite large. So this event, this explosion, is occurring in a region of the galaxy where there's not a lot of stars. So it's unlikely to actually have formed there. And in fact, it likely traveled from somewhere over here all the way to this distance. And that can take a really, really long time, up to a few billion years. So one of the things we do is look for this galaxy and try to identify the distance from the center of the galaxy to the GRB position. And this can tell us about what was going on in this system of two neutron stars before they actually merged. And we can sort of perform forensics on them and start to get an idea. So just to show a few other examples of host galaxies of short gamma ray bursts, here we see that it can be found in a spiral galaxy at a distance from the center of the host. So again, forming outside of the light of its galaxy, or in an elliptical host galaxy, where in this case, it's actually forming within the light of the host galaxy. So there's a lot of diversity within short GRB environments, and this diversity and the large offsets from the center of their galaxy were actually a really good indicator, even before 2017, that binary neutron stars were creating the short duration gamma ray bursts. But of course, that was confirmed by that merger. So one of the things that we've been doing with Lowell Discovery Telescope for many, many years now, and long before I came onto it, Brad was leading these efforts for a long time, we've observed all short GRBs visible from the northern hemisphere with the Lowell Discovery Telescope. And this was done to find their host galaxies, which can be really faint, requiring the sensitive capabilities of Lowell. And here we see a few nice examples. And this magenta circle is the localization on the sky of the GRB. We see some of them have more precise localizations than others. But in any case, we're finding these galaxies, and all these ones labeled G1 are associated to the GRB. And we're saying these are the galaxies in which the system of neutron stars actually formed in and then merged in. We see in a few of these cases, the distance from the center of the galaxy is pretty small, and this is okay. But when we look at the full picture, the full distribution of distances from the center of the galaxy, we see that it can be actually quite large. So let me explain what's going on here. If we look at this plot, this is the distance from the center of the galaxy in units of kiloparsecs, so 1,000 parsecs. And as we move this way in the distribution, these are systems that are at larger distances from the center of the host galaxy, where again, the offset is the distance from the center all the way over to this localization here. And we see for short GRBs, they're at really large distances from the center of their galaxy. But when we compare them to the longer duration GRBs, so these are ones with a duration of greater than 2 seconds, we find that those are actually at much smaller distances. And in fact, there's this separation between the two distributions, which is another way we can identify that it's different systems creating these two types of explosions. In short GRBs, it's the neutron star mergers, and in long GRBs, it's the collapse of massive stars, which should be occurring in star-forming regions, so where most stars are, which is towards the center of the galaxy and within the galaxy light. So the offsets are a good indicator of these two separations, but there's some other indicators as well. And in fact, we can use the environment and the host galaxy to classify events that are outliers to all of this that I've talked about. So for GRB 211211A, this is a new event from December 11th, 2021. It is a long duration gamma ray burst. The duration is about 50 seconds. And if we look here, we see this bright galaxy G1 at 350 megaparsecs, so pretty nearby to us. But the GRB exploded well outside of the light and at a large offset, which at first leads us to indicate that this is something strange because we're finding a long duration GRB in an environment that's very atypical for it. There's no star formation there. And in fact, the whole thing points towards a neutron star merger. And when we looked more at this event, we found that actually there was a kilonova signature detected, which is the smoking gun proof that this is the merger of either two neutron stars or a neutron star and a black hole. So this just goes to show that we can learn a lot from studying their galaxies. And in fact, they can point to us events that are outliers. So I'd also like to talk about the really new GRB from about 11 days ago, 221009A. It's the most powerful GRB ever detected, the brightest one. And we see here on the left a video of the GRB detection. This is not in real time. This is over hours or days, but from Fermi-Lat. So these are really high energy gamma rays. This is a space-based telescope. And here is a line that's showing the plane of the Milky Way. So this is a really wide field image. But at the beginning, we see right here that the GRB is the brightest thing on the sky at that point. So it's just that's a testament to how powerful these explosions are. The fact that they can become the brightest thing on the sky in just a matter of seconds. Another testament to how powerful and bright it is seen by this image from Swift X-ray telescope. So this is another space satellite at X-ray wavelengths. And here is the GRB, this sort of star here. And we see these really pretty concentric circles going outwards. So this is actually caused by the GRB being so bright that it's scattering X-ray photons off dust within our galaxy that it's passing through. And this dust is then being scattered again towards us, and we see these really pretty rings. And this is not seen for all gamma ray bursts. It's just a really bright X-ray source, and we can get this really nice picture and learn something about the distance to these dust clouds within our galaxy. And we're observing this source with the Lowell Discovery Telescope. This is an image I took on October 13th. The GRB is localized by this magenta circle, and we see it's really bright here. And then another image I took a few days ago on October 19th, we see it's faded. The image on October 19th, the weather was a little bit worse, so it's a little bit lower quality, but hopefully you can tell that there is a fading of this source. And I can tell you that it was a factor of about 2.5 in brightness. And we're going to be able to keep monitoring this source with LDT for quite a long time to come. And hopefully we'll see the emergence of a supernova explosion, which is going to show conclusively that this was the collapse of a massive star, creating this really long duration explosion. And that's everything I have to talk about. Thank you.
Oh, that's great stuff, Brendan. And again, just like with Erica, there's so many more questions to answer. That's what makes it most exciting. So let me throw a couple of questions your way. First of all, you mentioned using the LDT for a couple different things. It looks like maybe you use a large monolithic imager for those images. Can you talk about
Yes.
which instruments on the LDT you used and why those instruments were appropriate for that work?
Yes, so I was using the Large Monolithic Imager, the LMI, mounted on the Lowell Discovery Telescope. That I do use DVini for some sources, but generally the things that we're looking at are these really distant galaxies. And they're not bright enough to take really nice spectra like Erica was showing. If you have a bright source, taking spectra with DVini gives you the most information. But we really need a highly sensitive image where we can go really deep. And Lowell, being a 4.3 meter telescope, is, one of the biggest telescopes on Earth. And we're really fortunate to be able to use it because smaller telescopes just would not be able to achieve the science that we did with the short GRB host galaxies. We really had to even go to the sensitivity of this instrument to be able to detect some of these.
Okay, great. A couple more questions from Chris. Between long and short GRBs, is there a clear difference in net angular momentum of the systems?
So the long GRBs are being caused by the collapse of massive stars. We know that these stars have to be rotating rapidly, but I'm not sure about the difference in angular momentum. I would think that the merger of two neutron stars could be competing, but I don't have the numbers for that. Yeah,
okay.
It's a good question.
And then another one, have any of the recent GRBs been correlated to neutrino flux measurements at a statistically significant level?
No recent ones. This bright, really bright one was not associated to any neutrinos. It was associated with the highest energy photon ever recorded for a GRB at 18 tera electron volts. So that's another big story for this GRB that I forgot to mention. So we are seeing very high energy photons, but we're not seeing neutrinos at this point.
And is that something you expect to see at some point?
I think we can get neutrinos from GRBs, but I don't know how often we would expect that to be happening. Yeah.
Okay. Okay, thanks, Brendan. Gosh, we could talk all night about all these topics. There's so much great stuff. So let's now go to Brad. And we mentioned a couple instruments that Eric and Brendan currently have been using on the LDT. Brad's going to talk, among other things, about a new instrument that's going to be coming on board.
Sorry, I was muted there. Thank you, Kevin, and thanks to all of your colleagues at Lowell who do such a tremendous job continuing to operate this telescope that's really been a transformative resource for us in our science at the University of Maryland. You heard a really nice overview from Erica and from Brendan about some of the science we've been doing with the LDT in the last few years, even from Brendan just in the last few days. I want to tell a story about why I'm really most excited about the next 10 years of the LDT. As great as the last 10 years have been, I think the next 10 years are going to be even better. And to do that, I'm going to need to go back a little bit in time and give you a brief history of the 13.7 billion years of the universe in a single slide. So bear with me just for a moment here. If you imagine at the start, we have the Big Bang. All the material in the universe was contained in a relatively small volume. As a result, the universe was extremely hot. And any hydrogen atoms, protons and electrons that may have formed because it was so hot, because the universe was so dense, those hydrogen atoms quickly ionized. And so that we call sort of the first ionization stage of the universe. Eventually, as the universe expanded, it cooled. That allowed these protons and electrons to recombine to form hydrogen atoms. This was the first fundamental phase transition of the universe that we call the hydrogen recombination phase. And that's what you can see sort of around this blue line at the top of this figure here. After that happened, once we actually had some neutral hydrogen in the universe under the force of gravity, that neutral hydrogen was able to collapse to form galaxies, ultimately to form stars. And then we exited out of what we call the dark ages. This is why the top there looks kind of black in the part of this diagram. And those galaxies and those stars, of course, started creating light. And photons from those galaxies and those stars, they actually reionize the hydrogen, the bulk of the hydrogen that was in the universe. And this second phase transition that we call the epoch of reionization was really critical because any sort of neutral hydrogen is very effective at absorbing light and not allowing it to reach us. If we want to understand, the first stars in the universe, the first galaxies that were formed, understanding how and when this reionization happened is a really fundamental question and something that astronomers are really keying in on at the moment. So how do we do that? You can think, all right, you just look at the first stars, no problem, but they're really far away. Stars in general are pretty faint. What you saw from Brendan, the gamma ray bursts, on the other hand, unlike stars, are extremely bright. They don't last for very long, but that's okay. We can handle that. As Brendan mentioned, if your eyes could see gamma rays for their short duration, they would outshine everything else that's in the universe. And so what we want to do is to use these sources kind of as cosmic lighthouses. Imagine you have a very bright source in the background. It's shining light over in your direction. It's lighting up all of the material that's along the line of sight and allowing you to study everything that's intervening between you and that cosmic lighthouse, that gamma ray burst out in the distant universe, in order to understand what that material is and what kind of physical state it is in. And in particular, because you have these light coming along the line of sight, what it does is it can ionize material. And as it ionizes atoms of hydrogen, carbon, oxygen, nitrogen, whatever else is along the line of sight, those photons at specific wavelengths get absorbed due to those transitions. And gas that's along on the line of sight imprints these absorption features in the spectrum. You can see a sort of cartoon schematic of that here on the right. But these features are redshifted. They occur at different wavelengths than they would if we saw this happening in a laboratory on Earth, because different clouds of material at different distances from us are moving away from us at different speeds. And so we can compare the wavelength that we observe these absorption transitions to happen to what we call the rest wavelength, the wavelength where it happens in laboratories on Earth. And we can tell immediately how fast these clouds of gas or material in galaxies are moving away from us. And because we understand something about how the universe has evolved over time, we can actually use that to infer the distance to these sources as well. Okay, so that's some of the background here. In order to use these cosmic lighthouses in the early universe, when this epoch of reionization was happening, what's really important is that because of this cosmological expansion, because galaxies that are very far away from us are moving away from us very quickly, most of the light that they emit, which in their rest frame may be in the optical or even in the ultraviolet, gets redshifted down to longer wavelengths. And so for us, even though, in the rest frame that may be optical or UV, to us it comes out in the near infrared. And this is shown here. This is showing a couple of different spectra. So this is the amount of flux that's coming out at different frequencies of light here for gamma ray bursts at different redshifts, so different distances, ranging on the right from a redshift of 1, which in the scale of the universe is relatively nearby, over on the left here to a redshift or a Z of 20, which is very, very long ago, far away in the history of the universe. And what you can see is that if you want to look at reionization, which we know that happened at redshifts 7, 8, 9, 10, somewhere in there, we don't know exactly where, but somewhere in there, you really need to be pushing into the near infrared. You can't do this with an optical instrument. So you really want a nice, sensitive near infrared instrument that can respond quickly to these gamma ray bursts because they're fading away quickly. And so this is where RIMAS comes in. RIMAS stands for the Rapid Infrared Imager and Spectrometer. This is an instrument that is being built at the moment at Goddard Space Flight Center and the University of Maryland College Park. You can see it's nearly completed there, a nice recent picture from the laboratory on the left. What REMUS does is it allows us to take very sensitive imaging as well as spectra across the entire range of wavelengths that constitute near-infrared light. And it does this by using a dichroic, a beam splitter that splits light depending on what wavelength it has, sending it to multiple different detectors. That allows us to get imaging in different bands. It also does it using what we call sort of cross-dispersed to-shell gratings, where the light is actually sent across a grating and that's actually spread out into its constituent wavelength ranges. And we can actually see how much light at each sort of individual wavelength is coming out to allow us to measure a really detailed spectrum of these objects. And so what we ultimately want to do, you can see some examples of what's been possible thus far from gamma ray bursts. We think because we have this really nice instrument, because we really have this really nice telescope, and in particular, what's so advantageous about the Lowell Discovery Telescope is it allows you to mount multiple instruments at the bottom of the telescope at a given time. We don't know when a gamma ray burst is going to go off. They happen, once every few days. The ones that are at redshift that are relevant for reionization maybe happen once every few months or only a couple of times a year. But what's nice about the LDT is it allows us to have REMUS, it will allow us to have REMUS on the telescope all the time, so that whenever one of these things happen, we can interrupt what was going on at the moment and take one of these observations to measure the spectrum of a gamma ray burst at redshift 6, 7, 8, 9, 10 before it fades away too quickly. And this is an example of what's been possible here on the left. You can see this is not super high signal to noise. It's plotted the flux or the brightness as a function of wavelength. This is the highest redshift gamma ray burst that's been spectroscopically observed to date. It's at a redshift of 8. You can see right in the middle of the near infrared wavelengths between the kind of Y and J there. On the left, there's no light. This is all getting absorbed by neutral hydrogen. On the right, there's a strong emission coming from the afterglow. And what that allows us to do, in particular, if we get nice spectra, is to actually measure how much neutral hydrogen there is, so we can probe the neutral hydrogen fraction as a function of redshift along multiple different sight lines and really understand how reionization is happening. So as I said, we're finalizing this instrument. We're planning to install it hopefully in the next 6 to 9 months or so. And we really look forward to doing exciting science with it on the LDT in the next years and hopefully decade to come. So hopefully when we have the 20-year anniversary, I can come back and tell you all about it. I will wrap up there and gladly take any questions people have.
Well, that's great, Brad. Thanks so much. You said installation is in hopefully mid-2023. How long would commissioning be, do you expect?
Yeah, so we think that, the main commissioning would probably take, a couple of weeks if everything goes smoothly. The instrument, the hardware commissioning piece should be, knock on wood, relatively straightforward. Our experience with a lot of these is that, a lot of times the longer lead thing is actually getting all the software to operate the instrument successfully and, reduce and analyze and understand the data that we take. It's really hard to develop that software before you actually have observations to work with. And so that phase is probably going to take a little longer. But the actual commissioning, I think, should be, like I said, relatively straightforward.
And I think you've been pretty closely involved with the development of REMUS, right?
Yes, that's right.
And so can you talk about just how REMUS started, evolved, how long it's taken to develop it, and is that typical for an instrument sort of in this class?
It's taken a bit longer than we would have liked it to. The challenge is a couple of things here. The wavelengths that we are working at, if you want to observe in the near infrared, The detectors that we have to use are very different than the detectors that we use in the optical, right? The detectors that we use in the optical are the same detectors more or less that we use in our cell phone cameras. And so those are extremely well understood. They're well characterized. They're relatively straightforward to work with. That's not necessarily the case in the near infrared. So working with the detectors is challenging. The second thing is that to observe in the near infrared, you have to cool down to the detectors to very low temperatures, because otherwise just heat from the background would kind of swarm your images and not allow you to be as sensitive. So the combination of cooling the detectors, of working with the detectors themselves, has made this be a longer project than we would have hoped. But we are, I think, in a pretty good stage now where we should be able to get this on the telescope relatively soon.
Mm-hmm. And how unique is this, Remus in combination with 4.3 meter telescope? Is there anything comparable out there?
There are a couple of instruments. Yeah, there are a couple of other instruments. For example, on the Keck telescope, there's an instrument called NIRES that has a similar concept that can provide this cross-dispersed to shell, giving you access to the full near-infrared spectrum on a single with a single shot exposure. What is completely unique about the LDT is that Remus is on the telescope 100% of the time. At a place like Keck, right, you really can only have one instrument, at most two, on the telescope at any given time. And so because people want to use lots of different instruments, they'll only schedule, the near-infrared instrument, certain times of the month in particular, usually when the moon is brighter. But you don't know that your gamma ray burst is going to happen, that time of the month. And so what's really fantastic about the LDT is we have this resource. It's ready when we need it. We can call it up whenever we need it and go from there.
So how long would an observation be?
Yeah, it depends, on how bright the sources are. But for typical things that we expect to see, we're talking about observations on the order of 30 to 60 minutes, somewhere in that kind of range. Like I said, these are relatively bright sources, so they're very far away. So that it's not like they're extremely bright, but they're relatively bright. So we don't need extremely long exposures to do that.
And one more thing related to that: how much lead time do you have? Would you typically have between? Oh my gosh, this is out there. Let's observe it.
Great question. So the faster we can observe, the better. So typically these things, the afterglows that we want to observe, they fade like we would say as a power law in time. Okay, so what does that mean? That means every time you wait a factor of 2 in time, they get a factor of 2 fainter. So let's say, if you're able to start at 5 minutes versus 10 minutes after the gamma ray burst itself, it's going to be 2 times fainter at 10 minutes than it was at 5 minutes. It's going to be another factor of 2 fainter at 20 minutes than it was at 10 minutes. And so, almost every minute that you can get on is a precious one, because that source is going to be brighter the earlier you get on.
Okay. A couple more questions for you, Brad, then we'll see. I told you this time goes really fast. We're almost winding down, but a couple more questions. What's the design spectral resolution in the center of range?
Yeah, great question. So for the cross-dispersed to shell mode, the resolution, which is telling you effectively like how well you can separate photons with nearby but slightly different wavelengths, is about 4,000. And that's really tuned by, that's the kind of resolution that we need to actually resolve out some of the features that we want to measure the neutral hydrogen fraction. For comparison, Divini in the mode that we observe it in has a resolution that's, I think, around 1,000. Erica can correct me if I'm wrong. So we, in the spectroscopy world, we would call this kind of moderate resolution spectroscopy.
Okay, and another message from Chris. What kind of cryocooling system does the detector use?
That's a great question. I actually don't know the answer to that one. I did at one point, but I have forgotten at the moment. Yeah,
Yep.
I'm sorry.
And we're getting a few more for you. What's the scale of the Remus? How big is that? Can you compare it to something?
So that picture that you're seeing is probably, about a meter or, a yard kind of on each side. So it's not huge. It's not like it's taking up a big room, but it's not something that you're just going to be able to pick up and easily lift off the table either.
So this will be transported from Maryland to Flagstaff, hopefully this spring. What does that entail? Is that a pretty major thing, or considering the size, it's not like transporting a 4.3 meter mirror, but still?
Yeah, so it's definitely not like driving a 4.3 meter mirror across the country, fortunately. But we definitely need to be careful because there are, sensitive electronics in there, and so we don't want to harm those. So there are special freight companies that, are used to working with scientific instruments, and we'll hire one of those and we'll pack it up as best as we can and ship it off with them, and they will, presumably take care of it like it's our baby, because it is. But then, we obviously, that's the first thing we do when we get to the site before we actually put it on the telescope, is unpack it, check it out, make sure that everything kind of operates the way that we expect it will.
And you had mentioned that you're hoping, as we celebrate the 20th anniversary of first light of LDT, that you'll be back talking about how Remus has been working. What's the expected lifetime of Remus? Just kind of a general range.
Yeah, I think, without any upgrades, we expect that it should last for at least 5 years. It's possible that there may be some hardware failures after that point, but there's certainly, there's nothing in there that can't be relatively straightforward to replace, except the detectors themselves. And those we think should have pretty good lifetimes.
Okay. We've got just a couple other questions, also just a couple other minutes. And so I wanted to just jump in and say a couple things. We've been celebrating LDT all year, and tonight has been just a fabulous discussion on really the versatility of the telescope and its usefulness, not just the instruments, but the design of it that makes it so useful. And something that a lot of our guests are interested in is learning more about LDT. Well, next month, we're going to start doing tours of LDT where the public can sign up and go out there and see it firsthand. So I would just encourage everybody to keep an eye on our website for information about that. Also, we've received a couple donations tonight, which always helps the cause of Lowell Observatory of doing our science and communicating the science via scientific papers and through our fabulous public program. So thank you for those donations. And if anybody wants to make more and support the observatory and our partners, we really appreciate that. So we've got 2 more minutes. And so a quick question for Erica. If you can talk about the Einstein ring, and then we'll end it with a question that could take all night to answer, but we'll have about a minute. So.
Yeah, so Einstein rings are pretty interesting, and they result from large, massive, say, galaxies bending the light that's coming from behind them, so to speak. So if a galaxy is behind another galaxy, and that light from the behind galaxy is traveling forward, the light from the galaxy in front, or the mass of the galaxy in front, can bend that light around, and it'll result in the galaxy behind kind of getting smeared out in a ring. And so there's been a lot of talk about those recently because of the new JWST results and the new JWST images. So if you haven't had a chance to look at those, they're really pretty from JWST.
Yep. Okay, last question. In 38 seconds or less, one of you can answer this. How do we know there was a Big Bang?
I can answer that. We observed the relic radiation that we call the cosmic microwave background. That's a pretty telltale signature, and we see galaxies moving away from us, sort of uniformly, homogenously, isotropically on the sky. All of those are consistent with the Big Bang hypothesis.
Great. Well, we could certainly talk about so much of this, so more. It feels like we're just hitting the tip of the iceberg. But the time went fast. We're done for the night. So Erica, Brendan, and Brad, thanks so much for joining us. And thanks for the great science you and your teams are doing with the LDT. It's certainly an honor for Lowell Observatory to be able to collaborate with you all in your teams. And we all look forward to the future and the discoveries that are going to be made. So thanks for joining us tonight. And thanks to our behind the scenes team of Nate and Maddie for flawlessly operating everything tonight. And thanks for everybody for viewing. We'll see you next month as we continue to celebrate the Lowell Discovery Telescope.